Good morning. It's a great pleasure to be with you today. Appreciate everybody's efforts to put this conference together. I'm Habib Dagher, Director of the Composites Center at the University of Maine, and I welcome you to our first conference on infrastructure durability, sponsored by TIDC, the Transportation Infrastructure Durability Center. Hopefully everyone can see my slides. The Transportation Infrastructure Durability Center was established in 2018 under USTOT Region 1, and it includes universities from New England as well as states from New England. So we appreciate the Department of Transportation support that made all this possible. A bit about the center itself. It includes an advisory board as well as institutional leads. The advisory board is made out of New England DOTs, as you see from the Mass DOT, Maine DOT, Vermont, Rhode Island, Connecticut, and New Hampshire. And the chair of the advisory board is Dale Peabody from the Maine DOT. So we appreciate Dale and the entire team's hard work with us. We are keen on making sure that the research that we do is relevant to the durability needs of the New England states and the rest of the country. So their role is very, very important. We also have leads from each of the 6 institutions in this project or in this center. As you know, that's UMass Lowell, University of Rhode Island, UConn, Western New England University, and University of Vermont. And within the program, we have thrust leads that address each of the 4 thrust areas we have in the program. And you'll be hearing from the thrust leads throughout the day, and they will be managing the 4 sessions we have, the 2 in the morning and 2 in the afternoon. I'd also like to thank the administrative team who pulled all this together. That includes Jim Bryce that you see over here, who came to us from industry with a lifetime of experience in construction and bridges, and built companies that reached $1 billion in value. So great to have Jim here, and Amanda Colmore for helping organize. She's our communication director of this conference, and Vu Fan, who actually works with us on financing and grants. The Composites Center at the University of Maine is the host for the Transportation Center. We were founded in 1996. We've had over 2,600 students from 35 majors at UMaine work at the Composites Center. We're the largest research center within any university in the state of Maine. We have 250 faculty, staff, and students. And our annual research expenditures last year was $32 million. We're in a 100,000 square foot lab. We've had 10 spin-off companies from the lab. And a lot of visitors to the lab, over 25,000 visitors. So hopefully when Corona's over, we'd like to invite all of you to come and see the lab firsthand. These are our partners and clients from across the globe that do research with the Composites Center at the University of Maine. So you can see we have a wide-ranging set of clients. And the center has received national and international awards, over 40 of them, including the Champion for Change Award by the White House, the SCE Charles Banco Award, the ENR Top Newsmakers of the World, and so forth. What I'd like to focus on a bit today is what we've been doing on composites durability, composite materials durability. Back almost 12 years ago, we developed a technology called the bridge in the backpack, now called the composite arch bridge technology. That's been commercialized, and we have a company called Advanced Infrastructure Technologies that are building these bridges. These are essentially arches that are inflated out of composites, and they could be manufactured on-site or off-site and filled with concrete on-site. And then there's a composite decking that goes above, and then it's backfilled with sand, and the bridge is paved. What's unique is that we have been developing over the last many years a treasure chest of data for durability composites. We've built over 30 bridges using this technology across the country and outside the country as well in a variety of environments. You could see in this case, these are the arches that you see in black under the bridge, and they're filled with concrete, and there's a composite decking on top that's backfilled with sand. So this is a treasure chest of data, and one thing I'd like our researchers within the universities and others to really pour over this data that we started collecting over 2008, since 2008. That's 12 years worth of data on 30 bridges in a variety of environments, and study that not only today and tomorrow, but for the many years to come. This is what we're adding to that database. Just 2 weeks ago, this is a bridge that left the state of Maine on a truck. This is the arches. They were made in Brewer, Maine, and shipped to the state of Washington to build yet another composite arch bridge. So again, a treasure chest of data for researchers here that we can pour over and go back and evaluate these bridges, hopefully as a project through the center and beyond. But we haven't really only looked at arch bridges from a durability perspective. We have a lot of data also. Professor Roberto Lopez and Ida, working with the Maine DOT, have actually placed carbon fiber strands on the Penobscot-Narrows Bridge, and have been monitoring that since 2004. So one thing we'd like to do is continue this work and collect even more data on the performance of carbon fiber strands in this kind of environment. So there's a lot of data coming in on composites durability, and as we built this database, we're going to have the ability to go back to industry and to DOTs and improve codes and standards as we collect this data. But we have also data on composites in the marine environment. This is a boat we built for the US Navy SEALs. It's an 83-foot long high-speed interceptor, all made as a one-piece composite, carbon fiber with a carbon fiber hull. It's 83 feet long. So there is data also that we can pour over to help us better understand durability of composites. But one thing that we're really excited to work with you on, and all of us on, is really a new era of bridge construction and construction in general, is using large-scale additive manufacturing. This here is the largest polymer 3D printer in the world that we installed close to a year ago at the University of Maine. You can see here that's a gantry crane system that holds the extruder for the 3D printer. And it travels on a 60-foot long rail system, and can allow us to print things that are 60 feet long, 22 feet wide, and 10 feet high. But what's very unique about this is the printer head can be removed. This is an example of a boat that we printed last September, in about 3 days, in a weekend, a little over a weekend. It's a 5,000-pound boat, all printed in one piece. Now think about what we could do in civil infrastructure with technologies like that. That's really I'd like to challenge all of us to figure out how to work together to go in that direction. Another technology we've been working on that's been commercialized recently is called the CT girder. This is a composite girder that we've developed at the university, tested and proved out. And then this summer, Advanced Infrastructure Technologies will be installing a 70-foot bridge in collaboration with the Maine DOT. That's a composite girder that's quite a bit lighter, about the sixth the weight of a steel girder, that you put a precast or cast-in-place concrete deck on top system. So this is the bridge actually being manufactured in Maine, in Brewer, Maine. This happens to be a 72-foot mold, but you can see the bridge girder being pulled out of a mold, ready to be installed this year in Maine. To give you a sense of quite an unusual method of testing durability of bridges, this happens to be one of our partners at the Maine DOT. He's a manufacturing partner from the Maine Department of Transportation that wanted to see for himself what is the impact resistance of these so-called composite bridges. And so he took a sledgehammer to it, so I'll show you here a big sledgehammer going after a composite girder. Not a very common thing to do, but it gives you an example of how important it is for us to get these bridges out there so people could see them and use them and look for themselves. But this is a sledgehammer hitting the girder, the composite girder, and that's just a couple of months ago. Obviously, it did extremely well, and the DOT is very pleased. At least it did pass the impact test with just some paint scratches on the front. But what's really exciting for us, again, going back to 3D printing, the mold that this 72 girders has been built could be printed. And this is an example of a mold that we built for this girder. We 3D printed a mold independently of the mold you saw earlier. But beyond that, is that think about what we could do with complex concrete formwork for bridges, for piers, and docks and others. This is being 3D printed. The mold is for this particular girder. But this could be a form from concrete. The machining system, the printer we have, also doubles as a 5-axis machining system that can machine down to 5/1000ths of an inch. So imagine you can have very smooth formwork, of course, with this that's reusable and so forth. So one thing I'd like to challenge all of us, particularly the ASCE and Jean-Louis, I know he's thinking about this, and other DOTs, is how do we get some of these demonstration projects out in the US before we get them anywhere else in the world? And so let's find some places where we can actually utilize these new technologies, particularly for formwork. That's a low-hanging fruit for us to go out and build some formwork for complex bridges and show that we can do it a lot faster and get that done this year. So with this in mind, thank you so much for joining us.